Today we will talk about XGBoost. It's a scalable machine learning system for tree boosting. It has some advantage, namely handling sparse data, weight quartile, and column block for parallel learning. So first, advantage of XGBoost is the way it handling sparse data. So it adds a default direction in each tree node for the missing value, and the direction is learned from the data. First, we choose a default direction for missing value by calculate score when missing go left or right, and choose the highest direction. The key improvement is to only visit the non-missing entries, and the presented algorithm treats the non-presence as a missing value and learns the best direction to handling missing values. And the same algorithms can be also applied when the non-presence corresponds to a user's specified value, by limiting the enumeration only to consistent solution. The method exploits the sparsity to make computation complexity linear to number of non-missing entries of the input. As the result, it will make the algorithm faster. The second improvement is a direct theoretically suggestive weight quantile sketch procedure enables handling instance weights in approximate tree learning. The most algorithms before use exactly divided by split. We sort the data on values, then calculate all possible split options, which will make the algorithms computationally demanding. So, in XGBoost, we can use approximate algorithm. The algorithm first proposes candidate split points according to percentiles of feature distribution. The algorithm then maps the continuous feature into a bucket split by these candidate points, evaluates the statistic, and find the best solution among proposals based on the aggregated statistics, and it will make the algorithm distributable and recomputable. The last, uh, sorry, so it will based on the rank function, which will represent the proportion of instances whose feature value k is smaller than g, and the goal of the function is to find the candidate split points such that it's smaller than the rank value of the next one. So the last notable advantage is the column block for parallel learning. So the most computationally costly step is to sort the data. In order to reduce the cost of sorting, we propose to store the data in-memory units, which we call block. Data in each block is stored in a compressed column or CSV format, with each column sorted by the corresponding feature value. The input data laid out only needs to be computed once before training and can be reused in later iteration. The block structures also helps with using the approximate algorithms. Multiple blocks can be used in this case, with each block corresponding to a subset of rows in the dataset. Different blocks can also be distributed across machines and stored on disk in the out core setting. Using this sorted structure, the quartile finding step becomes a linear scan over the sorted column. It is especially valuable for local proposal algorithms, where candidates are generated frequently at each branch. The binary search in histogram aggregation also becomes a linear time merge time algorithm, and we can collect the statistic for each column can be parallels, giving us a parallel algorithm for split finding, and importantly, the column block structure also supports column subsampling, as it is easy to select the subset of columns in a block